Hey class, we're back with more of chapter 8.3, and here we're looking at example 2, which is drawing a 2D scale diagram that requires enlargement. So last video we looked at what happens when you need reductions. Now we're going to look at what happens when we want enlargement. So the scenario we have is that Jess designed the logo shown for an environment club. She wants to enlarge the logo so that it can be applied to the front of a baseball cap. The Hack Company has suggested that she use a scale factor of 5/3. Draw a scale diagram of the logo as it will appear on the actual baseball cap. So again, what I want you to do is kind of play along with the idea that this would be drawn on paper, and I want you to pretend that these measurements are actually 3 centimeters and this is 0.75. And what we're going to do is we're going to enlarge it. We're going to scale it up to the larger model. And what I would like for you to do is to pretend that this is actually the measurements that we get back. So you can see that I've already have one measurement labeled. What I want to show you is how I got that. So I'm taking my 3 centimeters, and what I'm going to do is I'm going to multiply that by my scale factor of 5/3. Now hopefully you can see that we have a 3 in our numerator and a 3 in our denominator, so those are going to create a 1. And so if this is 1, 1 times 5 simply leaves us with 5 centimeters. And so that's how I ended up getting this 5 centimeter measurement for my outer diameter. Now if I look at my inner diameter, I've got this little 0.75 centimeters. And so what I want to make a note of is at 0.75, I'm just going to reverse this and say that it's actually, I shouldn't say reverse, but I'm going to write this equivalently as 3/4 a centimeter. And the reason why I'm doing that is because then I can take my 3/4 centimeters and I can multiply it by my scale factor of 5/3. And again, you'll notice that I have a 3 in the numerator, 3 in the denominator. That's going to create a 1. So what I'm actually left with is 5/4 or 5/4. If you think about what 5/4 would be, that's actually going to be 1.25 centimeters. And so now I have this as 1.25 centimeters. And so that's as simple as it was. There's our enlargement. One thing I'd like to point out is that the angles were split up equal here. I don't think you could know that unless you actually read the problem in the book, but they were split up equal. So we have 360 degrees divided 3 ways. So each of these angles is 120 degrees. One thing that's really cool is that although the sides actually they maintain proportion, but they do get larger, the angles in similar figures actually stay the same. So all of these angles are still actually going to be 120 degrees. So that's kind of cool. So you're seeing that enlargement and reduction doesn't actually affect angles. Angles maintain their same value.